started developing an R package, which we called ESD in the start, because we used to do empirical statistical downscaling, but it's more involved into extremely simple, I think would be a better description of the package, and it makes it we developed it both because to make the code more reusable and more robust, but also to provide documentation so that we wouldn't forget what a script did a year after we use it, so we can reuse it. And it's more convenient to combine the scripts together with the documentation as well as sample data as well. So it contains both data, sample data, and that's why it's so big, because there's quite a bit of sample data and also help or documentation and the code itself, of course, and demo scripts to run some demos, and also to repeat some of the analysis we've done in some of the publications we've made. And also, before I start, I will also say something about downscaling. Basically, you start with some information, and you add more information, and then you end up with even more information and a better picture of what is happening in terms of local consequences to, like say, global warming in terms of temperature or rainfall statistics. So this sort of sets the scene for my talk. So ESD or R is we used it as originally used it as a tool to analyze connections in nature, and empirical statistical downscaling reveals dependencies between different scales, like say what is happening on a large scale and how that affects the smaller scales. And also it captures systematic geographical dependencies. So basically, if you think in terms of information, and that's the way I like to think about downscaling, is that we have already some information in terms of global model simulations, and they reproduce the connections that is described by the physical equations in terms of Navier-Stokes and thermodynamics and so on. But they are very crude, so they give a limited amount of details, and then we can add more information in terms of how the large scales and the small scales are interconnected, and also how the local geography affects the local, say, rainfall statistics or the temperature statistics. So then we add more information, and then we get a more complete picture. And the ESD package was meant to try to facilitate this type of analysis. That was the outset of it, and this is also what we did in the start, most of our analysis, but it evolved into much more after that. And the ESD package is very much inspired by this tool called Ferret that was developed by NOAA, Pacific Marine Environmental Lab. Because I used to be an oceanographer in the old days, and used to work with NetCDF more than 20 years ago. So we wanted to make something that worked a little bit similar to the Ferret tool, which was very easy to use and very quick to use. And my goal with this ESD package was that I could be able to provide some analysis while I speak with a journalist on the phone. So it should be very quick to implement, to do the analysis, but it takes, of course, a lot of time trying to design it in a clever way, and also to write the code so that it's bug-free. So ESD is now extreme simple data. And it's an R source package, which is available on GitHub, so it's open source. And also we have written some documentation for this package on the wiki page of the same GitHub page, and that also has some links to manuals and also like have some information about how to install it, and also so it's more like sort of tips how to use it. So it's a kitchen sink for numerical analysis, for instance, regression analysis, or it can also be used in connection with artificial intelligence. So it's designed in as a flexible framework, so you can use it together with your own models or your own favorite methods, such as artificial intelligence. So you can combine that with what is already there. So as I said, it contains both data and metadata and code and documentation. So one of the principles that we tried to implement was to get data straight into RStudio in a seamless way, so that it will take seconds to get the data in a ready format. So it's just to start applying various sort of analysis to it, rather than spending time to format data to make sure it's in right. Of course, we have to do that sometimes as well. If we get some new data, you can mold it into ways so it fits into the ESD structure, and then you can run all the functions and do all the analysis that you need to do. So, for instance, it reads netcdf files very quickly, and also it can read netcdf files from threads, so that's an opened up type facility. So you can basically read data over the internet, or it can also read ERA5 from CDS, so that's the climate data store from Copernicus. It takes takes a while because there's a lot of data and it's a bit more complicated. But there's a script that will do it for you, and it's not in one step, so you have to do it in 2 steps, I'm afraid. That's how it works. But also station data and indices, and it can also run scripts from Python and also import from Excel. And we use this package for evaluation and this visualization of the results. We've been working a bit with the visualization aspect to try to improve that. I'll give you some example data, and of course we could probably improve it further. And I would like to stress that if any of you use this package and have any questions, there's actually an issue page on the GitHub. So it's github.com/esd/issues. And the reason I want people to use that is because then if you have a question about the package, it's likely that somebody else will also have a similar question, and then everybody gets the benefit from the interaction we have explaining or trying to solve the issue. And it's very inefficient to explain things by email, because it's one-to-one. I like it to do it one-to-many, and it's much more efficient that way. So the thought behind both the ESD but also how we work is try to work in a very efficient and smart way, so that we don't have to repeat every time for everybody. And there's an advantage with common tools as well, because then we have discussions of problems and solutions that are common to everybody. And having these discussions is a form of quality control, and it benefits all of us, like even us who make the tool itself, because we learn from your problems and also the issues that you raise, and that also improves this tool. So it's constantly evolving. We keep uploading new versions, I think, every week with improvement, and like sometimes we find some bugs and then we have to improve it and solve it, and then and also sometimes we realize that we should include something more or some more functionality, so we do that as well, or maybe improve the documentation. And it's tailor-made for climate analysis, so and we try to make it user-friendly, and it uses a concept called S3 in R. So that means that we have very many different data objects. So you have like a time series, or you have like a gridded data, or you have like say a map, or you have a trajectory, or you have an UF. But all of these will work with the same functions. So when you write plots, it will decide what the plot would look like depending on what type of objects you have. And same with map as well, or subset, or UF. So you don't have to remember what type of object that you're dealing with, because these functions will be more generic, so they will actually be able to cope with the various types of objects. And I'll come back to that, because this is something that relates to smart data and how to set up a tool that can work in a sort of smart and consistent way. And also to use logical arguments. So all they should all have defaults if they can have. So it's easy to remember how to use it. So you don't have to sort of look up every time you want to use plot or map, like for what kind of arguments they have. So the arguments are what like the parameters we provide inside these brackets here in plots. So like plots and x. That would be the objects. That would be the first argument, and then there could be other arguments like what type of plots we would like to make, or whatever. And also this every time you apply a function to an object, it will actually include this step in a list of history list. So it will provide a provenance to the analysis. So the end result, you will have a list of what has actually been done to that object, before you get to when you get the end results, which is very useful, because that makes it very transparent what you've done, so you can repeat it. And then, of course, we want to make it so that the output of one function can be the input of the next function, or the same function as well. So you can have a chain of operations, and then so the output for one is the input to the next, and then we can even make a circle if you like. So it works a bit like Lego, as you see in the picture on the right. So you can you can build a more complicated set of analysis based on little building blocks. Yeah, and to give you one example of an S3 method. So if you have an object that is a station object, like it's called station, then your plot.station will actually will force that type of function. So, but normally you wouldn't have to specify .station, because it will find it by itself, because X would be a station object. So there would be the same as the same results, but sometimes you can force it if you want to make sure it uses that specific S3 method. So the seamless access to data. So here are some examples for climate indicators. Typically, we'd like to read the CO2 concentrations from Mauluna, and here X equals CO2. I think you would remove this default argument. So it's just an empty bracket, and the same thing in the next one. So if you have an empty bracket, then it will use all the default arguments. We wouldn't write that in the code itself. So the second one reads the Hadford 5 data, and it reads from the internet. So these are data that are listed by the various institutions. So you will read the most up-to-date data, and also the global sea level, even though that is not updated every month. I think it's a frozen data set. But it's like just for a plot X, so it's a very seamless way you say I want this data, and here from Norway. So it has a default. It will, because the data set is really huge. So when we have a default, we'll try to make it sensible. So it's not too big, so it shouldn't take too much time to read it. and then it will read it from threads as an open app. It's originally in netcdf, and then you can just plot a map of it to show what it looks like. So yeah, so this is open app. Another type of data is actually in the R package itself. Like, so if we and we can get the data that come with the ESD package by using the command data, and we want the storms, and then we say, okay, we want to make a map of subset of storms. And then here's one example. So here you see that the map looks very different to the one here, because these are different types of data objects. So this is a storm track, whereas this is like a gridded field, so they will look different. But you only need to remember, okay, I want a map of the data, so that's why we write map here. And here is another example. We want to read gloss data, so these are station data, and then we want to show a map. But here we don't want to like the default is to either show the location of the site when it's a station object, or like the mean values if it's gridded data. But we can also add, you can plot any sort of functions, like FUN is a function, and there's a function called trends, so then we can plot the trend, or you can actually define your own function first, and then you can call it from here. So then you can use the function of that you have defined. And there also we want to control and like what it looks like, so that we can, and then it has a list of various things there. And in this case, we only have one. So we specify it goes from -30 to +30, and then that step size 2. But this could actually contain other types of arguments as well that you can find in the documentation. Here's another example. It will we read metadata on threads. So now we are working with metadata rather than the data itself, and that's the strength, is actually to be able to work with both metadata and data. And here we provide a map of the stations that are stored on threads in Norway. So this is the example here, and then this is a map Abdulkader made for this presentation. So he sets the Y limit and X limit, and also the size of the symbols, and what type of symbols and what they look like. And then he adds the points, which are for Oslo Blindern, and then he adds that on top of it like this. And then we can use this metadata and say, okay, we can also get the data itself, and this is like a station number, STID is a station ID, and plot that as well. This is a cumogram, so it will plot the accumulated values over the year. So this is, I guess, and this will be only for the 12 first. I think this is monthly actually. So we can like just try, and it's easy to try and see what it looks like and then experiment with it. Here's another example where we read the 2-meter temperature from threads. So the parameter is 2-meter temperature, and station ID is for Oslo. And then we want the annual mean temperature, so that has annual, or sometimes we only use annual as well, so we use both of those. And then plot the annual temperatures here, and you can see that these are the annual mean temperature, and also add the lines as well here. So, and we also have started working with databases as well. So it's actually possible to connect R to many different databases. And then we can make RStudio as a window into the climate data, for instance, MariaDB or using SQL calls. And that's very useful because then you have a really powerful tool if you can connect R seamlessly to the database and then get it straight in. You don't have to fiddle around with lots of files and things. You read it straight. And of course, like as I showed, we can read ASCII data directly over URLs, as we did with some of the climate indicators, and netcdf files through opened app service as threads, as we did. Or you can import in RStudio from Excel files. I didn't show here, but we can also read data from Copernicus Climate Data Store, CDS. And this is one example. So you just write x equals era5.cds. So this is a function that reads era5 reanalysis data. So this is actually, so the first thing when we work with climate data is to actually get the data into R and get it structured or processed so it's ready to do the analysis. And that means that we combine data with metadata. And this is the idea of working with smart data, because then Map and Plot knows exactly what to do with the data, because we don't have to provide, we don't have to tell it exactly what to do every time, because it's already, the information is there, so it knows what to do with it. So it's basically the data structure and that has metadata. So here's one example. We have wind, and then we can plot the map with the wind, and then we can add the wind vectors on top of the map. And this is because this the data itself contains both the longitudes and latitudes, and also the times, and also what type of data it is, like whether it's wind or temperature or and so on. So this is ERA5 10 meters wind here, one example. So this is also one example of getting the data from CDS there as well. So here is another example with what we can do with visualization when we have smart data. So this is an animation of the temperature for every year. So this is the global climate model. You can see that the temperature increases, and this has been produced in R and RStudio. And this is actually the whole code I used to actually do the to produce this animation. So basically, we have to first start the R package ESD. So you do that with library ESD. So it activates the ESD package, and then we need another package called animation as well to make this an animated figure. And then we have to make a function which we call frame that will carry out some tasks. So basically, it will set the background picture to black and color of the axis white, and color labels white, the color main white, and then it will it has two parameters, x and it. X is actually the data, the grid data, and it is an index time. So that's one, and a parameter we use frequently in this ESD package. It is index time, is index space, how to extract certain times or a certain space. So this is like a time step that we want to take out, and subset takes out a smaller set of the bigger data. And then we want to estimate the angle, so it rotates. So it will go from, say, here it goes from 1 to n, and that's the length of the data file here. So you see further down here, this is where we call the frame here. Task is the annual temperature, which has been downloaded from the KNMI Climate Explorer. That's actually monthly data, and then we have calculate the annual mean data and then also anomalies with reference of 1961 to 1990. So these are like that's the baseline for this, and n is the length of this field data. And then we use save GIF, which is from the animation package, and then the frame, which actually prepares the figure, the frame, and also produces the map here. And here, it's the same function as we used before, but now we specify that the projection is a sphere, and and also the main title here is the year of the time step that we took, and then on the longitude for the sphere is minus r, so then it changes every time, and that makes it actually appear to rotate. And also we want to provide what we call starlight, so it has a shades here, so it's sort of more shade here. And then we set color by and this is actually possible because if you look at the task, that's the temperature. It's a time series, and then it has a lot of attributes that this is all the metadata, which is actually sort of tags of the data. These are sort of or labels that follow the data and don't get in the way with all operations, but they follow the data. So they give a description of what type of data it is, the longitudes and latitudes, and what's a long name and what kind of variable it is, and so on. So then this is actually what we call the smart data, is when you combine the data with like metadata that gives a sort of true description of what it is. And this is actually similar to the way that the files are stored in etcdf files. So this was inspired by the climate and weather the forecast convention, CF convention in etcdf files, that we read all the information into the computer memory, both the data and also the header, which contains all the metadata. So the data is on disk, they're stored in files, but in the computer memory they are data objects. But they have the same type of information. And there's been a lot of work actually done on the files and on how, like, the formats and the conventions and so on, but there's been less considerations when it comes to data objects when you have it in memory. And this is actually where R is a bit unique. I don't think there are many other languages that actually can facilitate the attributes in the same way as R. I don't think MATLAB did when I left it. It might do now. But it's actually very useful to have a common file structure, both in files, but also when it comes to data objects in memory as a smart data object, because then it's easy to use the same functions and also the same scripts to do the analysis. And that makes it the analysis much more reproducible. So here's one example of class and attributes. So class is basically the type or structure of the objects. So for the task as a temperature, air, surface, when you write class, you will see it's a field object, but also month, because it's a monthly data, and also zoo object because it contains time series. So that's from the zoo data library, which deals with all like leap years and all the dates and so on, which makes it very convenient to actually to work with the data. So we don't have to worry about all like, you know, like the different months are different number of days and so on. And then we have attributes of this data object. So these are attributes, and this is the metadata. And it has like how many dimensions it has, like index. That's the time, like the times it represents, but also class, and what variable, long name units, and longitudes and latitude and so on. And this helps the codes or the functions in terms of what to do with the data, and how, when it comes to making the maps or the plots or do the analysis. So then we can very easily just say, okay, we want a map of the data, and all of these attributes are hidden, but they are there. But that will follow the analysis and also make it more easy to actually do the analysis. So the benefits of that is that it simplifies the analysis, because it lets the code do most of the housekeeping, and it's much more quick and more efficient. So it makes it possible for me to talk to people on the phone and do the analysis while I talk to the journalists often, because if the data is readily available. And again, it uses the S3 programming style, plot, map, subset, and summary. And that makes it easy to search the data and sort it, but also extract information, because sometimes you have bigger data sets and you just want some of it. And again, it provides transparency and provenance and replicability. This actually runs up to the FAIR principle that was mentioned earlier. So, and I think there are not yet any conventions when it comes to the data objects, but there is in SCDF. But that makes it easy to collaborate when we have standard conventions. And one thing is like the field types that we have the NetCDF convention, but for time series there aren't so many, and then say storm trajectories, there are some conventions, but beyond that, often the data will come in all sorts of formats, especially like when it's ASCII based, and you have to write a new script every time you want to read it, and sometimes there's something goes wrong, and you end up with some bugs or some mistakes. So it's much better to have a convention, because it's quality controlled and tested and verified for the methods. And this is like also part of the smart data type of philosophy as well. So in the ESD package, we have the field, we have station, and we have events, and also now we have radio sounds. These are the sort of the basic sort of observable types, and the fields is basically regular grids, and this follows the CF convention. Stations, basically, you can have a group of stations. They are scattered in irregular coordinates. And then the event is basically when you have a storm someplace, and that is sort of moving, and it's not in a fixed place, but it takes place at some time. And radiosondes, which are also different because they represent a vertical profile of the atmosphere. And then we have derived objects, and these are the storm tracks, which follows the EMILAST. There was a project on mid-latitude storms. So it tries to follow the convention used there, but that was actually done in ASCII. So we also need to save that as in SCDF, because it takes much less space. So basically longitude, latitude, and then the identity of the storm, like the cyclone. So like you have like at some time you have one storm, and then you have a next storm coming, let's say a week later or 2 weeks later. And also the time as well. We also have other objects, IDFs, that's intensity, duration, frequency curves. So these are longitude, latitude, and then they have duration, so that's time durations that are lasting for 1 hour or 2 hours or 24 hours. And then also return time. So then it's like a 10-year return period or 100-year return period. We also have probabilities, like if you say we want to represent PDFs, and they represent like this temperature statistics at certain points, and then you have longitude, latitude, and then there might be a threshold value as well, like say the probability of temperature exceeding 20 degrees or more than 50 millimeters of rainfall, for instance. We have EOFs, which have longitude, latitude, and also then like the pattern. So like it's the first leading pattern or second pattern. So PCA, that's a principal component analysis. It's very similar to EOFs, but it's PCA applies to stations which have irregular coordinates, whereas EOFs applies to field objects which are regular grids. So the EOFs are like weighted in terms of the area of each grid box, whereas PCA are not weighted at all. So they are, so that if you have like a dense network of stations, at some point they will actually carry more weight than those in the periphery. And also we have results, which is all derived, different derived as well. And they also have to be smart data. Here's one example of like how the functions do the housekeeping. So we have Oslo, we have we want to read the station data, and then we have, if you write summary, so then it provides this type of summary that's useful for station data. So it's minimum temperature and maximum temperatures and mean temperature. So this would look different to, say, an ordinary, say, variable that would just give this for the whole set, but here you get a list according to the calendar month. And here's another example of invisible housekeeping. You get stations like within a station, and then you see that here the dimensions 134 stations, and you have 74,795 different days. And then we make a map. We want to see the maximum value here of this is the estimated temperature. You see that maximum is like 27 here in 28. So the one challenge is that when we have new data types, so, and this gives one example. So we have sea level pressure from ERA 5, that is also like a small sample that is provided by the ERA 5, the ESD package, and then we want to estimate the storms, so that's CCI, that's calculates cyclone identification. So that's another type of analysis we can carry out. And then we want to estimate all of these different locations we identify. And then you can see here, this is Hurricane Matthew that is identified from this sea level pressure from ERA 5. So this is hourly data. And then we have different type of attributes. And so this data object is different to the previous ones. And some of these are new objects that we have to experiment to try and find a sensible way to how to represent. So, and one of the things we want to do is to actually make the data so that they can be, like the output can be the input of the next analysis, and this is like inspired by Lego again. So the structure is of billing analysis with bricks. So maybe have 10 lines of R code using ESD that can carry out a finished complicated analysis. So there's one example. So you have you first read task as a temperature at air surface, and then we estimate the EOFs, and then we say, okay, once we have the EOFs, we can actually derive the field data from the EOF. So we can, it's a way of filtering data where we remove some of the noise, the higher order EOFs, because by default it will just keep the 20 leading EOFs. And then we can look at the difference between the original data and the data we got when we first estimated the EOFs, and then computed the field from those EOFs. I also had to deal with some of the attributes when we take the difference there, then the attributes don't always follow. So then we have to copy that attributes of task to the dtask, and so that we can make the map here. But actually here was an error. So then you had to see that, okay, the class was also not quite, didn't quite follow as well. So we had to set the class the same as task, and then when we do the map here, you can see we get the results there. So sometimes you have to make sure that the class and the attributes follow, they are actually the right ones here. So the metadata is the code part of the code part of the so part of code is actually you can sometimes the metadata can contain code describing how to operate on the data. So you can actually, in the metadata, you can say, okay, read me, like I have a readme attribute and say, okay, you have to run this R code on this data itself, and the code itself doesn't take a lot of space. It's actually quite small often compared to data. So then you can actually include the data and the metadata, the code as part of the metadata, and that is part of the data to bundle them all together. So then you can actually see, okay, I got this data, but I don't know how to do it. But here's actually a README thing. I can just run this part of the attribute to actually carry out the analysis. For instance, like if I have EOFs and how to expand it so it actually gets like the data rather than the information. And it could also be, the code is part of history of provenance to tell what has actually been done to the data as well. And the metadata is actually useful for searching, sorting, filtering. That I already said that. And then, of course, assist the analysis, regression, and classification. So general principles, what we always have to think of is like others will actually use our data, and that is so then that motivates using metadata and also like full description of what they are and use the FAIR principles. And I find personally, I find divided files really, really annoying, and I have some mixed experience with GRIB and shape data. And often when you get the data, you only get one of them. You don't get all of them. If you get them both, that's okay, but often you don't do that, in my experience. And of course, like then try to inject both data, metadata from files straight into memory, as you have in SCDF, and then you get the smart data rather than having like just the numbers, and then you have to match that with like other types of metadata. Because it can all be done in one go and in a seamless way, and you reduce the risk of anything going wrong there. So, and also I would like to say something about how we deal with ensemble data, because when we do the climate analysis in terms of model data, then we look at many model simulations. We should never look at one, but we should look at many ensembles, because even one climate model, if you run it many times with different initial conditions, just like a day difference, then you will get a lot of different realizations that will look very different over time. Say, and this is what Desert Al showed in 2012. Like even on decadal timescales, on a regional scale, like you will see that this natural variability will actually be fairly pronounced, and they get lots of different results. So then we need to actually look at more than 30 members of an ensemble, preferably more than 100. And the traditional approach is that we have one member has one file, and let's say therefore like as shown here, and that's a natural choice. But that's a very inefficient way of storing the data when you want to work with it. So this is like okay for a repository, but when you want to look at to do the analysis of data, then we can organize this information in a different way, which would dramatically reduce the data volume and increase the speed, and you only keep the salient information or that would be aggregated information. And I'll try to show you how that would work here. So here's a problem: like you have one data file, and we have like many grid points in each dimension there, and then we have many different maps. So it, like one data file itself, it's fairly big. And then we have many of these, and then we have more than 100 data files in Ensemble. And this, of course, takes up gigabytes of data, and then we'll think, okay, how can we deal with that in a way? Say if you have an R-Shiny app that is responsive, and that can actually dissect the data in seconds. And one way to do this is to reorganize the information in the data. So we use singular value decomposition, SVD. And this is the equation. So basically, set is the original data, and you can divide it into spatial maps and also time series, like one index for each map, and then a sort of weight that describes how much variance each map has. And it turns out that the number of maps that you don't read that many maps actually to describe most of the data. Maybe 6 maps or 20 maps to describe most of the variance. So then basically it reduced a lot of the dimensions of data by a huge amount, and then we can reconstruct the data but through this equation and get the original data based on say 6 maps and 6 indices and 6 weights. And it's a compression with some loss, but it actually, and it doesn't work for everything, but it works fairly well for at least when you want to visualize the data online. And this is a bit similar to what a JPEG does for photographs. So this is the one solution. So basically, we work on information, and the redundancy means that these maps are recurring. So the first map here explains most of the variance, and then these are the 6 maps that explains 99.3% of the variance of this data set here. So this is a different example, but so I just want to show this as in a clear way. And the bottom here are the time series, or the indices that explains how strongly these different maps are present at any time. So here's only 12 months there, and each of these curves represent different models. And so I just took 10 models there just for clarity. I could have had 100 as well, but you see that the leading pattern here has a very similar behavior for all of these models. And then when it gets further out, you get more noise and more differences. So this is like a way of compressing the information because there's a lot of redundancy, and basically we use this the mathematics. Here's the same equation. I just used different symbols here. Sorry, I made these at different time points here. And this is actually, this was supposed to be an animation. Let's see if I can. That's not working. But here's actually a paper describing this principle. So it's a strategy to effectively make use of large volumes of climate data for climate change adaptation. And you will also find a link to that also at the website here as well. So the ESD also works like when we work on analysis to look at connections between the various fields. So this is an example of using calculating a canonical correlation analysis between sea surface temperatures at the SFD and sea level pressure SLP here. And basically we have to read the data, and then we have to extract the right area we want to look at, and then estimate EOF from both, and then we use these EOFs as the arguments in the CCA analysis. And this example shows like the sea surface temperatures, how they are related to the sea level pressure. So this is pretty much the NAO signal here. And here's another example, like empirical statistical downscaling. So basically, the local climate depends on a mid-large scale situation. So this is a circulation pattern, sea level pressure. So you can use this dependency then to deduce consequences of global climate change here. So when we do the downscaling, we always have to do cross-validation. So we leave some data points out and calibrate the model and then try to estimate it, what the remaining points would look like, and repeat that so that we don't do that for all the data points, and then we plot these against each other to see how well they correspond. So there's an R correlation of 0.58. So you can see here it's also like the results. The black is the observations, and the red are the calibrated results. And this equation here shows the regression analysis. So it's a multiple regression here, where beta are the weights, the regression weights, and x's here are the principal components of the UFs, and y here is the local. So this is the rainfall amount here in Oslo. So yes, we also, if you want to read more about analysis and statistics in terms of common UFs and the UF analysis, there's also more in this paper, the perspective that we wrote some years back here in 2017. And the common UFs is actually a very nice way of comparing different data sets. So this example shows decadal predictions, and the black curve here shows the I think it was air interim for this region, and these red lines here show the ensemble members of the predictions, and they all these lines refer to this exact pattern here, and then you can see how well they agree, or if there's a big scatter, or if they follow the same trait, and you can see that they are somewhat similar. So they all show basically an upward trend, which is actually climate change, I guess, and also there are some indications that they capture some of the annual variations as well. I want to end by saying that there's actually more than just downscaling. And when it comes to climate change adaptation, we have three strategies. So one is stress testing, or what we call synthetic storms, or maybe even better, far-fetched storms. I'll show you that briefly. And then the other thing is sensitivity tests to see what is the most important for the system that I'm studying. Is it the rain or temperature, or what has the biggest consequences? And then the third one is the downscaling itself, which I've already shown some examples for. So for stress testing, it's highly non-scientific, but it's very practical. This is an engineer's type of approach. So what we do, we look at past weather forecasts. So we know some high impact weather events, and we can use those and just move them to a place that we want to study, and then look at the impact, like in terms of flooding and wind stress. And we can get data from the climate services, there's the Copernicus. So we can get it from the operational weather forecast, or ERA 5, if we like. So here's one example. So this is an analog for sort of worst case, where we look at wind and rainfall over the city of Khulna in Bangladesh, which is here. So we have weather forecasts for historical events, and you can see here, here is the wind, and so this and here's the rainfall connected to a storm. So we took Hurricane Matthew that was in September, October 2016, and it approached Haiti from the south. So we moved it to Khulna, just took the field over, and so we changed the coordinates, and because it also comes from the south there, and we can use this to sort of simulate what would happen if this kind of storm would hit Khulna, the city of Khulna. like what would people have to think about in terms of, say, flooding and, like, say, all these wires and things that hang on the pylons, like, and cables that be torn by flying debris. And that is how it's just a very practical way for, say, climate change adaptation to say, okay, what if this happened? And then the other thing is a sensitivity test. So we have, say, models for runoff or agriculture, or economy, or whatever, to test what is actually the most important aspects of climate for me. And in this example, we had a DSAT, so that's a maize yield model that Habiba Mtgori carried out with to see how the yields were affected by change in rainfall intensity. So what she did, she had the yield model and she had historical data. And we ran many times, but every time we ran it, we would say remove some of the rainy days, add some more rainy days, or we could increase the temperature or decrease the temperature. So it was like sort of Monte Carlo type approach, and we just changed the input and to see how does that affect the output in terms of crop yield, to try to find out what is the most important thing. So we see that for the change in rainfall intensity, it's not very big, but when it comes to temperature, we see there's a peak here, there's an optimal temperature, which is more, matters more. So that's this sensitivity testing. And then the last thing that we usually talk about is downscaling, which I already mentioned several times before, where we try to estimate how much rainfall will end up in this pocket from a global climate model, which has a resolution of 100 by 100 kilometers. So then we had to think of how to do that. And then luckily, and the rainfall for like the statistics of rainfall is quite predictable. And we can see from the global scale state, there's certain sort of typical patterns here where you have more rain along the equator and also storm tracks. So it's influenced by geography and it's fairly predictable and also useful, and that is useful for downscaling. And the two different types of downscaling, so you have dynamical downscaling and statistical downscaling. And I would use R to analyze both of these, but for empirical statistical downscaling, then the ESD package provides the means how to do that as well. And what we want to say to predict is how the probabilities change, like say this is the temperature, so that we can approximate that with a normal distribution, and also the precipitation, we can approximate that with the exponential distribution for just the rainy days. So you also have the wet day frequency as well. So, and there are, these statistical properties are actually fairly predictable and also fairly robust, and these are actually very useful for decision making. So often decision makers want a number, they don't want a time series. So that's so we try to downscale these parameters directly. That describes the shape of this curve. So this is a PDF. That's a probability distribution function. And this is actually not, that is the probability function here. So this is what they mean precipitation, which is the parameter that describes the shape of this distribution. And if that parameter changes from the gray to the red, you see that the curve changes shape as well. And the probabilities also shift with that. So if we can do that, then we can actually give some fairly robust answers to that. But when it comes to downscaling, and this is something that Abdulkader has done, is actually to compare the statistical downscaling with the dynamical downscaling. We want to combine them because they are based on completely different assumptions and different strengths and weaknesses. So we want to make sure that we have robust results. So we want to look at both of them, and in addition, we want to apply the empirical statistical downscaling to larger problems because they're very quick to run, so that we can also explore the range of results as well. And you can see that if you just pick up the like a small subset that's used in Eurocortex, it doesn't actually span the whole range of possible results. And you see you got lots of peaks there, so that you get, because you have a very small number of global climate models. So then you get the law of small numbers, which actually kicks in and can give you some misleading results or misleading statistics. So we run many climate model simulations, and like stress testing and sensitivity testing are really important to try to get a picture of how sensitive are we, and what would happen if this storm came here. But all of these things actually require new levels of evaluation as well. And traditionally, like the downscaling has been applied to a small number of global climate models, and also either DCM, dynamic downscaling, or empirical statistical downscaling, but not both combined together. And I think this is actually a unique Norwegian strategy that gives more robust results. I haven't really seen many others actually do the same kind of same range of different types of analysis. And now also we have moved into try to downscale the shape of these IDF curves as well, based on this equation here. So we downscale the wet day mean precipitation, which is mu here, and wet day frequency, which is FW here. And then we use these as parameters in this equation, and that gives some kind of representation that is sort of like a rule of thumb type of description of what the IDF curves would look like. And this is actually published also in ERL. So yeah, I want to finish off just to mention this discussion paper that gives an overview of all this sort of approach to downscaling, and also explains how, like, the importance of stress testing and the synthetic storms. So yeah, and then this is also like fun. It's a commentary on Reclimate about how climate change adaptation should be based on robust regional climate information. So that's all. And thank you for your attention. And